right, listen up. This is for all you new people. Rico's Rough Riders. We're gonna do some things here, but I'm gonna break you. Hopefully, some of you may know about this number or how to play with the vector off of the origin source or whatever. But
enter Albert Einstein. 1916. He publishes the general theory of relativity, the modern theory of gravity. In it, space and time is a fabric. Think of it.
Stop thinking. When you think about the planet, right? There's Neil deGrasse. He's the sunshine inside of it. There's on Earth. There's that. If he was in space, he would have things attracted to his feet by the mass. It might be, if angularly you put it close to him, it would be less attracted here because it's got to stretch to this distance, and everything in between. If it's coming up from this way, all that mass gravity is factorial 105 from center of mass outside of the back. So that's what they're kind of talking about when they say this Mercury in one of the fields of multivariable is...
Think of it as a deformable fabric.
Okay, so when we get to iron, right? When I talk about this version of it, think about it like the core of Mercury. Because of the amount of iron inside of there, it's going to be smaller. There's that much gravity from that center of mass. Well, not only is that its own fabric, but because paperwork works that way as well, we can say that the metrics inside of there was a combination of that Fe iron paperwork fabric and what hidden variable you didn't know about the core of what metal does what iron does in the core of Mercury, of that scale of it. But supersymmetry works that way because it's the fabric. It's the way you're about to describe the calculations in 45s that gives it a general state away from this special relativity variance of it, that when you think about special relativity, trying to recreate Venus or Mercury or this field theory that you produced, the special relativity is when you're going to do that exact same field theory, but you're going to second law the thermodynamics every single part. Even if they wind up being the same calculation, you just change the number to reference this other thing, and they are weakly attracted by each other. The fact that, there might be some trip on light years, however that innate hack with space works, moving faster than light. But back to iron, in a field, FMA, against this wave at the top end of the spectrum, I do believe it's radio waves move the fastest, or gamma. Ultraviolet would be the fastest, tightest bandwidth before all that drag of the long wave function slowed it down and redshifted it. But that's kind of like light bumping into particles. There's a supernova with a planet in its way. It's going to cast a shadow until, if it was far enough out, it would always cast a shadow. But if that was inside of the supernova that just sanitized it into carbon out there in space, you would see a shadow and then this gray zone, right, before it just goes straight to white. You see the light again, but it would always still be gray shifted a little bit because of the initial surge of the supernova that was expanding out into where it was when you could observe it from that. Well, that's like light hitting an air particle, or a particle in space, or another wave function. Now, they weakly interact with each other. It's kind of meshing through, but to determine its full luminosity as a particle, you're still looking through a lot of space, while particle of how it got there. Did it hit anything? Is that now changed? That fabric is deformable. That the FMA was there, we know the inverse of it had to be some sectors of the field inside of there, and now how are we recreating it? Because if you just go blindly about field theory in that nature, sure, you'll derive field theory, 1 equals 1 equals 0, whatever it is, but you're not really gauging it to that 2, or why t is a fourth dimensional object. It's still 1/2 from 2. We're just saying the xy in this grid and the xy in the next grid, or photon and gluon, or however you start that. Start with the gluon to make the observation as a photon. Some doesn't have mass. I mean, here's a picture of it, but it's not until we add in those points which have mass, the real values of the increments that we're putting in. And math is that trippy thing like that. So I hope you're hanging with me today. And that to mathematically simulate this, I would need a ball that is shorter, squattier, and wider to add gravity to then say, well, that centrifugal force is going to pull up the equator and it's going to rest, or the prime meridian, and the equator is going to then, because of that spin, start to contract, much like Mercury's core, right? If you do the math wrong and say, well, its observations doesn't do that, well, at the state of gravity, they're compacting, kind of like iron in a star that goes neutron star, right? You're just saying that the star had all that iron in it, it decays to iron, and then it condenses to a black hole, which isn't the same object. But what do we know about blue hypergiants or red giants about to go supernova? There are real observations about those things that say, like those aspects, like those supersymmetries, like the time dilation of having to know that point where epsilon is equal or less than 0, or equal, in that form, that says the way you progress this is a 45. When I'm talking here, it's saying I'm trying to get you from an origin source to 1 where x and y are both 1. And that's a longer distance. It gets me just that little bit in front of it that says, now that I know this dot plot, or I could do this dot plot or try to be in that way, I'll have a better insight on the next step. And that's progressive. It will run to an end when you finish the project and it runs its cycle, because like cycles or periods, bases to those ideas, that's the kind of factorial pattern that's not really a pattern. Mercury's orbit had changed in some way, but the obloidic orbit of it is still within the same parameters. They're not wildly variating and having that effect. And if there was, you would see why. It's like, well, that's a better observation. Not just that it was already had a hidden variable in it, but now affected by another source, which any source will do, but this one was plenty enough on the scale of things that it would need to act upon. So weakly attracting, you put a ping pong ball next to it, it will affect, but not well. So that's my note.
And gravity is not a force between two objects. Gravity is the shape of that fabric. And bodies move according to where that shape tells you to go.
Z is Y, and Z can also be
And when
X.
you factor in all the tenets of relativity, what we found is that Mercury was following the severely curved fabric of space and time.
Right. So, again, not only, remember when I was talking about iron? Well, that was all hydrogen. You can see how deformed it would be. Even though the gravity was what it was, these orbits were going around. We didn't really think about the tidal forces of the moon. We knew the moon was around, right? You know it's around right now. That's that fabric. That's very deformable. I could add the moon. I could take out the moon. If I add the moon, I'll have something more relative to the observation as the planets and us on it are doing. But if I take it out, I have this really neat math problem that might be relative to a situation where you have to say, in order to derive the information, I have to take the moon out of the equation, probably by adding it in to zero it out to see what other variables are there. And that'll give me this framework, this one-dimensional math and two-dimensional metrics with a three-dimensional field, and, yeah.